All right, so the next type of series that we talk about the convergence to is a P-series. A P-series is a result of the integral test. If it looks like 1 over n to the p, if p is bigger than 1, it converges. If p is less than or equal to 1, it diverges. If it's equal to 1, it's got a fancy name called harmonic. Okay, so the first one right here, you see if I think of it as 1 over n to the p would be 1/2, so it diverges. Here, p is 1.2, so it converges because it's bigger than 1. Again, bigger than 1, so it converges. And then less than 1, so it diverges. The next ones are trying to determine what values of p would cause it to converge. If you think about these two pieces right here, that's what's really telling you everything about the series. So that looks like this. So basically, you can compare it to 1 over n to the p minus 1. If I want this series to converge, which would be your comparison series, we need this value in the power to be bigger than 1. So p would need to be bigger than 2 for convergence. Same thing here. This looks like a P-series. I would need this power to be bigger than 1 for its convergence. The next ones are talking again about what values of P would cause us to converge. But looking at this one right here, notice we have n only in the power, so that looks geometric. If it's geometric, R, the thing that's to the power n, has to be less than 1 in absolute value. So that would cause P to be either less than -4 or greater than 4 for that to happen. And again, think about that. Those are the ones that we're looking for. We want this to be less than 1. So if this P was smaller than 4, then this ratio is going to be bigger than 1. So you need this to be bigger than +4 or less than -4. Same thing here. If we're talking about what's the most important thing, you have an n up here, and down at the bottom, if you imagine multiplying this out, it would be called 2p. So that our power is really 2p minus 1, and for convergence, I need that bigger than 1, which causes p to be bigger than 1. 11 was a typo. 12, which one of these converge? This is -1/2, so we move it down to the bottom. It's a divergent P-series. The next one right here, if you move this around, this is really e to the -n, 2e to the -n, and then you can move those around. The negative exponents go to the opposite side. So that tells us r is equal to 2 over e, which is less than 1. So this one also converges. And number 3 is a P-series, p to e, which is bigger than 1. That also converges. So all 2 and 3 both converge. And the next set was again still in the P-series, and they asked which one of these infant series converge. So looking at this, it's got the negative n, so we can bring that down, and now that's geometric. Look at the only variable is in the power. R is 1/3, so this converges. This looks like 1 over n cubed. That's what you would compare it to. 1 over n cubed converges, so either by LCT or DCT, and again, LCT is going to be the easier. This one also converges. This one, p is equal to 1/5, diverges because it's smaller than 1. So the only ones that converge are 1 and 2. So same thing, bringing this down, p equals 3 converges, p equals 1 diverges, p equals pi, that converges. This one's not a P-series, this one's geometric. Notice that the n is in the power, not in the base. Same thing here. I think this is the same as that problem. I just kind of accidentally typed it twice. Or I saw it at 2 different places and didn't notice it. And let's see, 16. Which one of these are a divergent P-series? Well, this one's geometric, converges. Divergent P-series, convergent P-series. This one is actually divergent nth term test because the limit of that is not 0, which causes it to diverge by nth term test. And which one of these are harmonic? Harmonic means that it's a P series with p equals 1. This one's not harmonic because it's not the entire 1 to infinity. So this one's your harmonic. This would also be referred to as harmonic. In fact, anything that looks like 1 over a n plus b is going to consider harmonic.